Hello, my name is Mahjouri and I'm a junior at Auburn High School. In this presentation, I would like to discuss my project on generating energy from wheel motion by designing a hybrid 3D printed triboelectric nanogenerator. Currently, the drastic increase in fossil fuel consumption and greenhouse gas emissions by gas vehicles has led to the rapid rise in manufacturing electric vehicles, also called EVs. Besides eliminating the exhaust emissions, EVs become even greener as they move toward the use of renewable sources such as wind power and solar energies. However, a significant problem in these vehicles is the energy storage and consumption efficiency. The driving range of an EV on full charge is limited, so the vehicle must constantly be recharged, and this is both costly and time-consuming. So far, various methods have been considered to address these issues, including solar cells. Solar cells harvest the wasted energy from solar radiation and convert it into electricity to charge the batteries. Although this is a potential green solution, solar panels can only harvest energy when the sky is clear, and this is not ideal for different locations, seasons, and times. Another method, called regenerative braking, works to recover electrical energy when the driver either takes their foot off of the accelerator or applies the brake pedal. However, when driving uphill or on straight roads, the accelerator pedal must constantly be used, and this therefore drains the battery. So the ultimate interest is to find a method to harvest energy as the wheels are in motion to power the batteries and other electrical components. My solution to potentially address this challenge is to employ triboelectric nanogenerators. So what is a triboelectric nanogenerator, or TANG for short? TANGs rely on two major principles, including the triboelectric effect and electrostatic induction. The triboelectric effect occurs when two materials of different electronegativities, one is said to be electronegative while the other is electropositive, interact with each other. At the interface, the electrons of the electropositive material transfer to the electronegative. Now, when the two materials are separated, a potential difference is induced between the high and low potentials. Attaching electrodes, such as copper tape, and wires to each material mirrors the principles of a capacitor. The circuit allows the electrons to flow from one side to the other to form a net neutral charge on both materials. This process essentially discharges the capacitor through electrostatic induction. By repeatedly touching and separating the two materials, the tank can continuously generate power. Therefore, due to their low cost, environmental friendliness, and high conversion rate, tanks are ideal for powering electric vehicle batteries. Now, the goal of this study is to fabricate a practical hybrid 3D printed wheel-based triboelectric nanogenerator that can harvest wasted energy from a moving wheel in electric vehicles. In this project, computer-aided design software and a 3D printer was used to customize the design of the wheel prototype in order to maximize the harvested power output. Aluminum tape was used as the electropositive material, whereas PDMS was used as the electronegative material. The copper fabric serves as an electrode and is attached to the PDMS films. Lastly, a tablet oscilloscope is used to obtain waveforms and data about the output voltage produced. The procedures of this project consisted of two major steps. The first was to make the triboelectric nanogenerator. To do this, a silicone mixture was cured and coated on top of a piece of copper film, and this serves as the electronegative portion of the tank. Aluminum tape was cut into pieces, and this serves as the electropositive portion. To create the wheel structure, CAD software was used to model the design, and next, the model was printed and brought to life using a 3D printer. Finally, the tangs were attached to the wheel by alternating between silicone and aluminum, which is represented through the yellow and blue colors on the rendered design. This slide aims at demonstrating how the wheel tank would function in a real-world setting. As the electric vehicle is in motion, the tangs constantly come into contact and separation, thus producing continuous electricity which charges the battery. The next step in my project was to create an electric vehicle prototype in order to test the viability of my design. I used two wheel tanks in my prototype and connected them together in parallel. A breadboard consisting of multiple LEDs was attached in front of the prototype to serve as electric vehicle headlights. This video shows LEDs turning on as I bring the prototype into motion in a very dark room. The bottom two pictures are snapshots of all the LEDs being turned on. To test the prototype characteristics for applications in the real world, I decided to conduct an experiment on the average output voltage produced versus the vehicle speed. It is seen as the speed is increased to 3 meters per second, the output voltage increases linearly to about 10 volts. The next experiment was testing the effects of the Tang surface area versus the voltage produced. And it is shown that as the Tang width is increased, that the output voltage also increases linearly. And this is because the more air you have, the more chance you have for charge accumulation at the interface. The last experiment was the effects of applied force and impact frequency on output voltage. And it is at first seen from about 0.5 to 1.5 of forces, newtons, that the output voltage increases linearly. But after that, it starts to level off. And this leveling off occurs since, at a certain point, the PDMS has already interacted with all of the aluminum microstructures, so it cannot produce more voltage. This waveform depicts the voltage produced over time of the Wheel-Tang prototype moving with a speed of 3 meters per second. A peak-to-peak voltage of 10 volts is clearly seen through this picture, and this waveform was extracted through my tablet oscilloscope. In conclusion, I was successfully able to design an innovative Wheel-Tang prototype that integrated the principles of the Triboelectric effect and electrostatic induction in order to harness energy from the otherwise wasted frictional energy. The project proves to demonstrate the real-world application of the Wheel-Tang in electric vehicles to increase their driving range. In the near future, I aim to improve the Wheel-Tang output by 3D printing a better wheel design for the wheel and also identifying new materials that have excellent electrical properties. In addition, I plan to design a proper electronic interface to integrate tangs into the battery of an EV and test their performance. Thank you very much for your attention, and I hope you have a great day.